In this video, I want to talk about specifically a Next.js backend. Now, Next.js is a very popular, started as a front-end framework, but of course it's now a full stack framework. And pretty much every other open source project, if you see, they end up using Next.js, and for good reasons that we will explore in this video. Now, the reason I want to cover this topic is Next.js, and especially Next.js when it's deployed on Vercel. Vercel is the company which created the open source framework called Next.js, and Vercel is the infrastructure, is the cloud infrastructure which hosts different front-end frameworks. Now, Vercel is the infrastructure where a Next.js code base runs on. And when you deploy a Next.js code base in Vercel, there are a lot of things happening behind the scenes. And the Next.js framework was designed keeping the developer experience in mind. And for that reason, the way you write code, the way you interact with your data, the way you expect pages to be rendered, and everything, they follow a specific synchronous pattern so that it looks like everything is connected and everything is happening in a very synchronous manner. But behind the scenes, a lot of things are happening to make all this flow happen as smooth as possible. And people, engineers who are starting out, especially engineers who are starting out as front-end engineers, and of course they eventually get into Next.js because that is one of the most popular frameworks. And in that transition, it's very difficult to understand the backend side of it, the infrastructure side of it. And that's not always a bad thing. You can build a lot of things without understanding all the infrastructure that goes on. But of course, if you have a solid understanding about what's happening behind the scenes, then you can be a better developer, you can build better projects, you can build powerful projects by utilizing all the workflows behind the scenes, by understanding how everything comes together. So with that, let's start. Now, one of the primary technologies that Next.js and Vercel uses for the infrastructure is serverless. And this term is used a lot, and it's often not completely understood, especially if you are coming from a front-end background. So that is the reason we will be covering all the basic concepts, not basic, and that is the reason we will be covering all the foundations that you need to understand in order to wrap your head around how Next.js and Vercel infrastructure actually works. And we will start with serverless, the primary infrastructure component which Vercel uses to host and to run your Next.js apps. Okay, a bit of history. When we started out with internet and with servers, usually companies used to build their own infrastructure. They used to have their own data centers, they used to have their own servers in their own premises, and that's how they used to host websites and host servers, etc., etc. And eventually, of course, that model, we quickly outgrew of that model when cloud technologies and platforms like AWS, GCP, and Microsoft Azure, these things were introduced. So instead of going too much into the on-premise infrastructure, we'll quickly start with the cloud infrastructure because that's where the interesting parts start. So what happened was, whatever infrastructure that was initially on premises, all of these things were moved to cloud technologies. Right? The transition happened and we reached it. And here also, if you want to host something, you want to host a server, if you want to host a website, of course, you are going to need servers. So even though we moved to cloud, which just means that instead of having your own device, your own server, your own hardware, you are renting a hardware of some other company, some other provider, and you are doing it over the internet. That's all about cloud. That's the definition of cloud in the way. Now, in the cloud also, we need hardware, we need servers to deploy our servers, to deploy our websites, static, dynamic, etc. Now, when we're talking about servers, cloud computing providers, right? Providers like AWS and GCP, they provide some abstraction models to run your code. Now, the first thing is virtual machine. And this means that operating system that you will be given access to, they will be running on top of a hypervisor. And we'll come back to this term, what is hypervisor and all. To just simplify a bit, virtual machine just means that there will be an underlying technology. In this case, it's called hypervisor. And its job is to provide some CPU, some RAM, some disk, and a operating system kernel. Its job is to provide some hardware resources to a completely isolated environment that is going to run on top of the existing hardware. It is going to assign some amount of CPU, some RAM, and some space in the hard disk from the host, etc., right? A complete isolation over an existing hardware. That's what a virtual machine means. Now, since it is a complete isolation of the hardware of CPU, RAM, and hard disk, booting up a new VM, a new virtual machine, takes a lot of time. A lot of time does not mean it takes minutes and all, but it takes a few seconds. Seconds that is significant when you're talking about latency over the internet. Right? Now, the second abstraction model is the second abstraction model that we get are containers, such as Docker, etc. And this technology, this container technology, like Docker, they use OS level virtualization. OS level means they are functioning on top of your operating system. So this is one level high. Previously, it was, let's say this is your hardware, whatever hardware you have available. And on top of this, you have your virtual machine. Now, when we are talking about containers, either they can, let's say you also have a host here. You're not running on top of a hypervisor, you're just installing an operating system on top of your hardware. There can be two paths. Either you're running on top of a hypervisor. Now, a hypervisor comes somewhere around here. Its job is to assign hardware resources to operating systems. Now, container technology, that comes somewhere around here, containers, right? They run on top of a existing operating system. We are one level high when it comes to the abstraction level. And the way the containers work is the package, the app, its dependencies, and they run in an isolated environment. But they share the kernel, the host, the operating system that you have installed, which we call as the host operating system. It has a kernel. And the way containers work is all the containers share the kernel of the host operating system. So that can be considered a security vulnerability, but we won't get into that. We just want to understand all the abstraction levels at this point. Now, if we are one abstraction level on top, this means that the latency we were getting on booting up a new VM, booting up a new virtual machine, that won't be there. And that's the reason booting up a new container is significantly faster than booting up a new VM, booting up a new virtual machine. We are talking about milliseconds. And this is what we mean when we say compute. We explicitly assign some amount of hardware. We choose the level of virtualization, either to hypervisor or to a container technology. Yeah? And we deploy our server, or we host our web pages, etc. This is the traditional way. This is the, or you can call the serverful way, because you are explicitly maintaining your hardware. The second way is serverless. And this is the term that we have to understand first. Now, serverless, what it does is it goes one step further and it abstracts away servers entirely. that is the goal of all the cloud providers with the serverless technologies. Now here, what the idea is, you will just write the code, whatever logic that you want to run, and you will decide what is the event trigger. When should this logic, let's say you have written some kind of logic. You've defined what is the event that should trigger this logic, and you write the logic, and that's it. You say deploy this function. Whenever something like this event occurs, I want to run this piece of code. That is the whole idea of serverless technology. Instead of saying I wanted 2 GB RAM and a dual core processor and 30 GB of hard disk space, etc., etc., you just say that this is the code, this is the logic that I want to run, and this is when I want to run it. And that's it. You don't mention anything about the hardware that you want to run on. Right? That is the idea behind serverless technology. That you don't explicitly worry about the servers that are running behind the scenes. These cloud providers, these serverless platforms, they completely eliminate the need to provision or manage servers explicitly. The function that you define here, whatever the logic you want, this function starts when this event triggers it, and when after some time, after it is successfully run, whatever server, of course, you cannot actually run something, you cannot actually deploy your code and expect it to run without managing, without assigning a server, some kind of computing resource to it. But the point here is you won't be doing that. Your cloud provider, whatever serverless platform that you're using, they are going to decide what kind of compute is going to be assigned to this piece of code, and how is it going to assign, when is it going to assign, and when is it going to be taken away from. The key idea behind serverless technology is when your function is not running explicitly, computing resource is not going to be assigned to it, and in turn that saves some cost for your cloud provider, and in turn it also saves some cost for you. And that is one of the primary motivations of coming up with the serverless technology, and it's also one of the reasons serverless technology is so popular these days. Now, to give a little bit of history, AWS, the AWS cloud platform, it is one of the first cloud providers that came up with the serverless technology, and it started offering it, and it called it function as a service. And it launched this technology, this service called AWS Lambda, which is the serverless technology of AWS around 2014. Initially, the Lambda serverless technology, it only had support for Node.js. You could only write Node.js code that will run in these serverless functions. Around 2015, it was available to general public, and because of the reason that Lambda only supported Node.js, JavaScript initially, it did not have support for other languages. There were a lot of criticisms, but eventually AWS added support for Python and Java and other runtimes one by one because of the popular demand. And after AWS, cloud providers like Microsoft Azure and GCP, Google Cloud, they also followed, and they also launched their serverless platform in 2016. Microsoft Azure had support eventually for C# and JavaScript, and Google also launched their serverless technology with Node.js. Eventually, they added more runtimes, etc., etc. That's about the history of how these serverless technologies and when these serverless technologies were available to us. The next interesting part to note here is, what is the catch? If these technologies were so revolutionary and they were so cheap, then why did it not change the complete infrastructure of internet? The reason is there were some pain points, and one of the major pain points were cold starts. So what do we mean by cold starts? Cold start basically means when this event occurs, this event that you have mentioned beforehand, that whenever this event happens, I want to run this logic. right? I want to run this logic. So whenever this event happens, this in these serverless platforms, what they have to do, they have to first prepare your execution environment. They have to download your code. Maybe they have to compile it if it's not pre-compiled, etc., etc. And after that, it finally runs. So before the code starts to run, there are some steps involved. And because of that, there is some kind of latency, and that latency is called a cold start. So if we go here, and so if we come to the docs for Lambda, we can see here that whenever you hit your Lambda endpoint, whatever event that is supposed to trigger your Lambda, there are certain phases that follows before your code is finally invoked. At this point, there is a extension framework for Bliss that is supposed to be initialized first, then the runtime, the execution environment where your code is supposed to run on top of. If it is a JavaScript, if it is JavaScript code, Node.js code, then a Node.js environment has to be prepared first. If it is a Java code, then JVM has to be prepared, etc., etc. Right? The runtime has to be prepared first. Then the function initialization. So in a typical Lambda code, you will first initialize whatever, you'll import whatever you want to import. You'll write some kind of initialization code, and finally there will be an handler where you will write the actual logic. So this initialization code that you write, that is the next step. So this whole initialization phase, this is what we mean when we say cold start. And because of the model that serverless says, it does not assign servers, actual physical servers beforehand to run and to execute your code. It only assigns a server, some kind of computing resource when it is actually needed. So that is the reason we have to go through this cold start phase. And after the function is completely run, there is a runtime shutdown and extension shutdown, and all the runtime, all the environment that was created is completely destroyed. Now, of course, there will be some kind of grace period. And by grace period, I mean, if for every event trigger, all these initialization phases, the extension initialization, runtime initialization, the function initialization, all these cold start causes, if they were triggered for every event trigger, then that would completely defeat the purpose of saving computing resources. The only reason we came up with the technology serverless was we wanted to save computing resources. We wanted to save cost by not running actual computing resources unless we need them. But if we do all these expensive operations every time an API is invoked or some kind of event happened, then that would waste a lot of resources. And that is the reason after your code is run, the Lambda will not shut down immediately. The environment, the execution will not be torn down immediately. There will be some kind of period when it is still there in case another event occurs or another API is hit, right? Then that instance can serve it immediately. And typically we call that as a warm instance. Cold is when server resources are not assigned yet. All these phases has to be done first. That's when we call it a cold start. But if a server resource is already assigned, then we call it a warm instance. It is already there for us to serve. Okay, that's all about cold start. And that was one of the primary pain points of why serverless did not see so many adoptions when it was first introduced. When AWS first announced Lambdas, it used a technology, its own service, which is EC2. And EC2, if you are already familiar with the service, it's a very popular serverless compute based service in AWS. And EC2 uses VMs. In the start of the video, we talked about different types of isolation technology that cloud providers use to let users on their platform use different types of computes, and EC2 is one of them, and it uses the VM isolation level. And as you already know, VM internally uses a hypervisor based abstraction, which means that you have a hardware set, you have some amount of RAM, some amount of CPU, some amount of hard disk, and you install some kind of hypervisor technology. And if you want to know some examples, VMware is one of the popular examples of hypervisor technologies. We also have VirtualBox, right? These are called hypervisor technologies, and what they do is they take the hardware resources, and for each virtual machine, for each VM, you select a particular operating system, and they assign some amount of CPU, which you choose, and RAM and the hard disk, and that operating system with that set of hardware resources is completely isolated from other VMs that you share the hardware with. The core kernel of an operating system is not shared because the abstraction level is on top of an hardware. And because of that, booting a typical VM takes a couple of seconds. Because if you have noticed, any operating system, if you've used Windows operating system take a little bit more time, a couple of seconds if you have the advanced hardware, and Mac also takes a couple of seconds. Linux operating system, especially the ones without a GUI, they are a little lightweight, so they are a little faster to boot, but still the couple of seconds of booting time is constant in any type of operating system because of the number of features they come with and the level of isolation they come with. Now, the reason we are talking about this is initially when AWS released Lambda, it used to boot up a new VM using its EC2 service for each Lambda invocation. And because of that, the cold start time that we were talking about, it was around in seconds, and that was a big problem. And it halted the adoption a lot because most of the architectures in the market were serverful architectures, and people were not ready to trade in this couple of seconds of cold start time every now and then. Initially, we also talked about another abstraction level, which is containers. And containers work on top of an existing operating system. They share the kernel, and whatever container that you run on top of them, they run as isolated user space processes. That is still some kind of isolation, but container level isolation is not considered as secure as VM level isolation. VM level isolation, which works on top of a hardware, that is considered more secure because hypervisor technologies do not have as many security vulnerabilities or as frequent security vulnerabilities as container technologies do. If you follow the news on vulnerabilities and all, you will notice containers often face different critical security vulnerabilities. So since these cloud providers like AWS, GCP, whatever serverless platforms that we are talking about, the reason they are providing the service is because they want to take some user code. You have some user code here, any abstract user code. They don't care about what kind of code. They want to take any user code and they want to assign some kind of compute here. And they want to run this user code. And because of this whole expectation of taking any abstract user code and running it in your hardware, and the fact that this whole thing, taking the user code, assigning some computing resources and running that, this happens for a lot of users, thousands of users, millions of users, especially if you are a big cloud provider. Given that your platform is basically a multi-tenant platform, we call this architecture this architecture of having multiple users use your software or your hardware. This architecture is called a multi-tenant architecture. Given that as a cloud provider, you have a multi-tenant architecture, security is one of your prime responsibilities. So you cannot make the trade-in with containers, that since containers work on top of an operating system kernel, you cannot make that trade-off and go with the container technology for your abstraction level for running abstract user code. Container technologies, their booting up time is in milliseconds, right? It's almost insignificant. You cannot do that as a cloud provider for security reasons. That is the reason using containers for reducing cold start time was not an option. Finally, on around 2018, Bliss came up with a new technology called Firecracker. And if you want to check this, Firecracker is also an open source repository, which is of course maintained by AWS. And you can see the code, you can see the source code. And as you can see, most of the part is written in Rust. Rust is very useful in very low latency expected environments. And we'll talk about what Firecracker is. And the whole idea was, as a serverless platform provider, they wanted something secure, and at the same time, they wanted something which minimized the cold start time, which is a big hurdle for companies to adopt serverless technologies. And that is the reason they came up with this technology called Firecracker. Now, Firecracker is not a complete invention. It built upon something called as a KVM. KVM basically means a kernel-based virtual machine. If you search for Wikipedia, it says that KVM means kernel-based virtual machine. Now, a typical virtual machine which assigns a new kernel, a completely new operating system for each instance of the virtual machine. Kernel-based virtual machine is basically a hypervisor, the technology which is responsible for assigning these hardware resources to different VM instances. That hypervisor runs on top of a single kernel. And that is the reason we call Firecracker, whatever the VMs that are created by Firecrackers, we call them MicroVMs. They are not our typical VMs. They are called MicroVMs. And the reason they are very fast is because in a typical VM, you have some amount of hardware resources. You boot up a new operating system that takes new drivers for interacting with hardwares and a lot of bloat that comes in a typical user-friendly operating system. But for running code, for booting up an operating system which is not expected to deal with any kind of user, human is not going to interact with your operating system. Given that requirement, what AWS made the trade-off with was, it came up with a technology which worked on top of a kernel, and it boot up these micro VMs, which was stripped off of all the unnecessary drivers, all the unnecessary features of an operating system, which was not needed if a human was not in the loop. And that is the reason they were able to come up with these very lightweight VM instances, and they called it micro VMs. And as expected, they were very fast. They were still secure because they were still a VM at the end of the day. They were not containers. The isolation level was still as strong. It was very high performance. As you can see here, it was measured, the starting time, booting time was measured in milliseconds. It is 125 milliseconds. And it's also open source. So given the requirement that you are a cloud provider running a multi-tenant architecture, taking thousands and millions of users' code and running it on top of your hardware, having that piece of your technology open source brings a lot of credibility to you as a company. And Firecracker has a lot of security modules built on top of the existing KVM technologies. This big change, AWS Firecracker MicroVM technology, with the introduction of this hypervisor technology of microVMs, the biggest problem in serverless technology, which was the cold start time of seconds, it was brought down to milliseconds, and that significantly helped with the adoption of serverless platforms. Now you had all the advantages, all the pros of using a serverless based architecture without making a lot of trade-off when it comes to occasional latency of cold start. Now we are talking about cold start of 125 milliseconds, which is not a lot if you are a platform, if you are a SaaS platform which gets a lot of traffic. In that instance, given how serverless platforms work, if you get a lot of traffic, so let's say we have a timeline here, and some this we can call this T0, this we can call this T1, this 2. Assuming that at T0, your computing resources, your platform was idle, you are not getting a lot of traffic. But assuming at T0, you got some amount of traffic, say around 50 HTTP requests. After this point, as your traffic grows, eventually your serverless instances will also scale with them. That's one of the properties of serverless architectures. They auto scale with your demand of the traffic, and from this point onwards, whatever traffic you get, they are not going to experience a lot of cold start time, because all these requests, they are going to come and your platform, your backend is going to serve them. And after they are gone, let's say 50 more requests come. But at this point, the assigned computing resource, the serverless instances behind the scenes, whatever that was assigned in a Firecracker VM, they are still around. So all the subsequent requests that come immediately or a little later, when the computing resources are not turned down yet, they can still reuse whatever computing resources were assigned to the previous set. That's the reason in a high traffic environment, serverless instances do not typically experience the cold start time because of the nature of how they work. Since we are talking about the timeline of 2017, 2018, around the same time, another big piece of technology in the serverless ecosystem was also introduced, and that was Cloudflare Workers. And this is the blog post from 2017 where they announced Cloudflare Workers to everyone. Now this technology, the technology on top of which Cloudflare Workers worked, they brought a completely different POV to the discussion of isolation when we are talking about a multi-tenant architecture, when we are talking about running user code on your hardware. They took a completely different route, and a very interesting, a very efficient route also. What they did was they used JavaScript V8 engine, which was built by Chrome. If we look it up here, you can read more about what is V8. V8 is basically the JavaScript engine that Chrome uses internally, that Chrome built, Google Chrome built, and it also uses internally to run JavaScript inside your browser. Whatever JavaScript that is executed in your browser, that is run using this engine. It is very efficient and it's been around for a long time. Now, what Cloudflare did was it used V8, and V8 has a very interesting feature called isolates, which is a sandboxing feature for running user code, any kind of abstract user code inside your browser. Now think about this. Browsers have been around for a long time, and what a browser essentially does, it shows you websites, it shows you HTML, CSS, and JavaScript. Basically, to oversimplify it, it fetches all these resources from remote servers, and it renders all these HTML, CSS, JS together, and you can see different web pages. You can interact with them using JavaScript, etc., etc. That's what a browser typically does. Now, the point to note here is a browser fetches JavaScript code that is written by users, millions and millions of other users who have written code. And what is the use of a programming language? To interact with a system, in an expected manner. Now, a browser fetches abstract code written by other users, and it fetches them and it runs on your system. And if you think about it, that can be a major security vulnerability. If you're fetching thousands and thousands of users code and you are running it on your system, that is a huge security risk. That is the reason, if when we are talking about sandboxing basically means containing the scope of a program or whatever execution that we are doing to a limited environment, which is completely isolated from the host that you are running it on. And in this context, what I'm trying to say is browsers, when we are talking about sandboxing technologies, browsers are the greatest of them all because of the nature of how they work. They fetch millions and millions of other users' code and they execute on your system without affecting your host operating system, without affecting your system where the browser is installed on in any way. The sandboxing technologies that browsers use is top notch. They have gone through years and years of research when it comes to security vulnerabilities and when it comes to sandboxing efficiently, etc., etc. And in the same way, the V8 engine built by Chrome, it also has sandboxing support and top class sandboxing support, right? Years of research, years of vulnerability based research, years of bug bounty programs has gone behind it. And with its sandboxing features, it also offers explicit sandboxing and abstraction feature called isolates, which basically means you take some amount of code that you want to run. And in this case, in serverless platforms case, it is the code of your user. And you want to take that code and you want to instantly spin up a instance of that code in a contained environment, which is called an isolate. And because of how lightweight this nature of these isolates are, and at the same time secure because of the robustness of Chrome V8 engine when it comes to sandboxing, you can spin up hundreds and thousands of isolates in a single process, in a single system, because of how lightweight and how efficient they are. And if you take a look at all these properties that Chrome V8 engine was offering, it was a very good candidate for being considered for a serverless architecture. And that's exactly what Cloudflare went with. They used V8 when AWS used Firecracker and a MicroVM based architecture for the isolation level of their multi-tenant architecture for a serverless platform. Cloudflare, another cloud provider, which was majorly targeting the CDN space. And we'll get back to CDN, which is another important piece of technology to understand the Next.js backend. Cloudflare was one of the major CDNs around that time, and they wanted to introduce compute into their edge nodes. And this is what Cloudflare went with. They went with using V8, Chrome's V8 engine, as their serverless architecture host. And this is the blog post where they announced how exactly do you write an worker. It's just JavaScript code. And what are some of the APIs that you can use, like the inbuilt fetch API? What are some of the limitations of these workers, etc., etc. This blog post does a deep dive on all those concepts. Okay, now let's try to track down the different behaviors of the two major serverless platforms that we are currently talking about. One is AWS Lambda, and here we have, and it's not that there are not other cloud providers who offer serverless technologies, but since we are specifically talking about Vercel infrastructure and Next.js backend, and they behind the scenes majorly make use of AWS infrastructure and Cloudflare infrastructure for different pieces of technologies. We are going to discuss these two to get a comprehensive understanding of how Vercel internally works. Okay. Now, we already talked about Cloudflare Workers. They ended up choosing Chrome's V8 engine. V8, and here what we have Firecrackers MicroVM. Here we have V8 isolates for the abstraction, for the isolation technology behind the scenes. The second thing is, because of how efficient Chrome V8 was in executing code and spinning of new instances of that code, a very revolutionary idea, a very revolutionary offering that Cloudflare came up with was a 0 millisecond cold start. And we've been talking about cold start a lot, and you can understand that this offering of saying that you have 0 milliseconds of cold start changes the game completely. Cold start is one of the major hurdles for adopting a serverless platform. And when you're saying that you get all the advantages of a serverless architecture, a serverless platform, and you have 0 milliseconds of cold start, that changes a lot of things. At the same time, Firecrackers, even though they had a very small cold start time because of the Firecracker architecture, the MicroVM architecture that is built on top of a Rust runtime, they still took around 150 milliseconds sometimes if it's a large user code and it required complex runtime requirements. Then it also went till 1000 milliseconds. Now, talking about the cons, Cloudflare Workers, since they made use of Chrome V8 engine for running user code, it was of course limited to JavaScript. You can only write JavaScript and you can only run JavaScript in a Cloudflare worker because internally it uses V8 engine and uses JavaScript engine to execute your code. At the same time, since AWS Lambda, it is still a VM based technology, you can run a lot of programming languages. You can run JavaScript if you want, you can run Python, you can run Go, you can run Java, whatever you want, whatever AWS Lambda platform is offering. Now, that is a major advantage here. Not all companies, especially big companies, have a lot of code, a lot of resources, a lot of employee resources in a diverse range of programming languages. They still work with a lot of Java code. They still run a lot of legacy code bases in Python, etc., right? So not a lot of companies can afford to move existing infrastructure, existing computing, existing code to JavaScript. Another thing to note here, especially in the Cloudflare workers based runtime, if you're familiar with Node.js code, if you have written Node.js code, this is not the same as Node.js. Whatever JavaScript code that you are going to write inside a Cloudflare worker, that is not going to look the same as a typical Node.js code. And one example is the file system. You can use the file system in a Node.js runtime, but you cannot do that in a V8 based runtime. Right? You don't have access to the file system. And that is for fair reasons. In serverless based architectures, you don't want to give file system based access to your users. So that actually works in the favor of Cloudflare. And this also has a lot of other features. Basically, the idea is whatever code that you can execute in your browser, you can only execute the same code in a typical Cloudflare worker because the browsers behind the scenes use V8. Of course, Node.js also uses V8 behind the scenes to run JavaScript, but it also builds a lot on top of it to provide file system based access, to provide TCP sockets, etc., right? It has a lot of features because Node.js is a server runtime that people use to build servers on top of one. But V8 does not need to cater to that requirement. It has a completely different set of requirements. That is the reason in a typical Cloudflare worker, in an edge runtime, we will come back to this term is edge compute or edge runtime. This is going to be a very important concept, and we are going to come back to this very soon. It's very important to understand this part to understand how Vercel and Next.js work. Okay. And in an edge runtime, when we'll be talking about edge runtime and edge compute, V8 plays a huge role there, because typically edge computes and edge runtimes use V8 because of the isolation, because of the security level that it provides, also because of how efficient it is, how efficient and how fast it is to boot up new V8 instances when we are talking about isolates. Also the reason that how less of a resource that a typical V8 based architecture consumes. It consumes very less RAM, it consumes very less CPUs, and it is highly optimized. Because if you think about it, browsers, the Chrome browser, a typical Chrome browser is expected to run in a very high-end hardware like a MacBook M4 Pro, and at the same time, it's also expected to work in a, let's say, an Android set from 10 years back, which does not have a lot of RAM. It has around 512 MB of RAM as compared to the MacBook M4 Pro, where you have 64 GB of RAM and state-of-the-art operating system, etc., etc. So a browser has to optimize a lot, tweaks, it has to make a lot of space for efficiency. Those kinds of behaviors also reflect when you're using a V8 based runtime in edge locations. Now that we have a good understanding of AWS Lambda based serverless architecture and Cloudflare Worker based serverless architecture, now we are in a good place to talk a little bit about Vercel, because that's our end goal, to understand how Vercel and Next.js work behind the scenes. Recently, Vercel introduced Fluid Compute, the compute-based architecture that Vercel uses behind the scenes to render your pages, to serve your API endpoints, etc., etc. That we are going to talk about a little later. Now, what Fluid Compute does is it builds on top of AWS Lambda, of course, but it also adds a lot of infrastructure level features to that to make resource utilization more efficient and more fast. Because a couple of things that it does, and if you go through the blog that you can read, but I'll summarize it here to make it faster. Now we are talking about Vercel Fluid Compute here. A couple of things that it does. First is pre-warmed instances. Now, as we already know, in a typical serverless based architecture, cold start is one of the major hurdles. Now here at this point, now that you are aware of it, you can say that why not go with Cloudflare Workers? Because Next.js is already a JavaScript framework and Vercel wants to decrease the cold start time. It wants to make it more efficient. Then why did Vercel not use Cloudflare Workers behind the scenes to make the cold start time 0, since Cloudflare claims and Cloudflare offers, of course, this feature that you get 0 milliseconds of cold start. Why not Vercel use that? Because Vercel wants to offer Node.js runtime. A Cloudflare Worker offers edge runtime. Edge runtime basically means you can only run that code which you can run in a browser, which means you cannot use file system based APIs, you cannot use a lot of crypto based APIs, you cannot make TCP connections to external servers, etc. So there are a lot of limitations. But Vercel offers Node.js runtimes. You can use all the features of Node.js in a typical API endpoint that you build using Next.js. It also offers edge runtime that we are going to talk about a little later. But given the requirements that it also has to offer Node.js runtime, it cannot just go with Cloudflare Workers. It has to go with AWS Lambda for its serverless architecture. And that is the reason it came up with this efficiency mechanism of pre-warm instances. It basically means that instead of when the event triggers and it has to run your code, and it has to assign some amount of computing resource and it has to run your code, what it does is it keeps a pool a pool of already assigned computing resources beforehand, and when a new request comes, it tries to make use of those existing computing resources, those pre-warmed instances, because if an instance is not ready with computing resource, we call it a cold instance. And if it is already prepared, if the instance is already ready to execute your code, we call it a warm instance. So what Vercel does, it keeps a pool of pre-warmed instances. So when a new request comes, it can quickly assign one of those instances, and the code will have very minimal cold start time. Pre-warmed instances is one of the things that Vercel Fluid Compute does to minimize your cold start time, especially when you're server rendering your page or you're serving an API endpoint. The second thing is something called bytecode caching. Bytecode caching basically means when an event triggers, let's see here, let's say a trigger happened, then it has to download code, then it has to compile your code. Of course, JavaScript is not a compiled language, but still, whatever JavaScript runtime that is executing that code, it still has to output some kind of machine code that it can execute. Since JavaScript is a high-level language, high-level dynamic language, there has to be some kind of machine code that has to be executed. That's what we mean when we say JavaScript compilation. And whatever output that it gets from here, it's called bytecode. And this bytecode, if you have a function and it was executed once, it was triggered once, and it was executed once, then whatever bytecode that is obtained from that execution, what it does, it caches that bytecode so that the next time the event is triggered, it does not have to go with all these steps of downloading your code, compiling your code, and preparing the bytecode, then executing it. It directly can jump to the execution phase. That is another efficiency, that is another optimization that Vercel offers with its fluid compute model. And by the way, fluid compute behind the scenes uses Rust-based runtime to do all these things, to assign resources and do a lot of different stuff. And since Rust is a system level language which is highly optimized and very safe and very fast, that further decreases any amount of latency that you're going to expect if it, let's say, used JavaScript to do all these different kinds of stuff. Now the third thing, now this is a very important thing that offers a major advantage over other serverless technologies, which is optimized concurrence. Let's understand this with this scenario. Let's say we have a timeline here, and this is T0 and this is T1. So let's say at T0 some event triggered or an HTTP request was made. That's why Vercel triggered this serverless instance. And at this phase, your program, your code started to execute. But after this point, as you already know, most of the things that we do in a typical traditional based backend is interact with other components, and that is called IO, right? Input output model, IO. And IO is very different from CPU bound operations. IO is basically you made some kind of request to either a local device or a remote server, and you are basically waiting for the response while that comes, and you're not doing anything else. Right? IO is something that wastes a lot of CPU cycles. And because of this behavior, what Vercel did to not waste CPU cycles while your serverless code is waiting for some IO response, either from an API call, from a database call, etc., etc. Right? During this whole time, when it was sitting idle, it was not executing any code, it was just waiting for some kind of response. What Vercel does in its fluid compute model, it brings some other serverless code instance, and it tries to execute that code in this time when your existing serverless code is waiting for some kind of IO response. To make use of those CPU cycles, it brings in some other serverless code and executes that. So in a way, it tries to optimize for CPU cycles, but by not wasting it. And whenever it detects that some code is waiting for some IO operation, then it tries to make use of those CPU cycles by not wasting it. And when this IO response is complete, at this point, your program will again start executing, right? Here it was blocking, and again here it will start executing. Or if after the IO it is finished, then the program will return, you'll get the response, etc. Now, this has a major impact on your cost also, cost savings. This is the fourth advantage in the Vercel fluid compute model. And why does it have cost advantage? Because here, our traditional serverless platforms, in let's say when you're talking about AWS Lambdas, right, the way they charge you, the way they monetize is, once your function started executing, once your function is invoked, all the time from T0 to T1, they take this whole amount, whatever time it took from T0 to T1, and they charge you based on this. Does not matter what happened between T0 and T1. They don't care about that. They charge you based on when your function was executed and when it stopped executing and it returned. But what Vercel Fluid Compute does, it offers another cost advantage to users, that you will only pay for that time when your code was actually executing. So at this point, when your code was waiting for some kind of IO response, you don't pay for that because you were not using the hardware resource, the CPU cycles in this instance. And because of that, you don't have to pay for this. So what Vercel Fluid Compute model does, it actually goes through the program execution phase and it tries to find out all the time slices between T0 to T1, from the moment your function started executing to the moment your function returned. From T0 to T1, it finds out all the time slices when your program was actually consuming CPU cycles, and it charges you based on that. So as you already know, in a typical backend architecture, IO takes the largest amount of time when you're waiting for some external response. And this pricing model significantly saves a lot of cost because of that, because of how typical backend systems work, because of how IO works, because of how CPU cycles work. Right? And that is another big advantage. And the reason Vercel is able to offer this is because while your program was not using this, Vercel took some other program instance and started executing this. So in a way, it did not waste any resource. And that's the reason it is able to give you that discount, because the platform Vercel was also able to save some cost and it wants to give that advantage to you also. And so these are some of the advantages. These are some of the features of Vercel Fluid Compute, which of course builds on top of AWS infrastructure, AWS Lambda infrastructure, but it also brings a lot of its own infrastructure, its own components, its own optimization techniques on top of it to provide all these features. Another thing that I want to note here is the idea of serverless. Now, this is not directly related to Vercel, but since we are talking about serverless, the idea of serverless is not just limited to compute. Since we were talking about Lambdas and workers, Cloudflare, it is not just limited to compute. It spans across different infrastructure also. Because if, for example, if we are talking about storage, we have two different options. We have object storage and we also have databases, of course. In object storage, we have technologies like S3 and we have R2 object storage from Cloudflare. And when we are talking about databases, we have Amazon RDS, we have Amazon DynamoDB. We also have external serverless database providers like Neon, PlanetScale, etc. Same way when we are talking about other components of a backend, say we are talking about a queue, a pub sub queue. There we also have Amazon SQS, or we are talking about a notification service. There we have Amazon notification service. Now, one thing that you see in all this, one thing that is common in all this is they're not compute. Of course, they're not compute. You don't have to think about execution and all. But traditionally, when we used to think about deploying or hosting a database over the internet so that our servers can use it, in those instances, what we did was we took some kind of computing VM, let's say an EC2 instance, and we installed a database server on top of it, let's say Postgres or MySQL, and we exposed that, and we manually managed whatever database maintenance, whatever database migrations, backups, replicas, sharding, etc. Everything on our own. We took some kind of server, some kind of hardware, and we built our own database management infrastructure on top of it. And which is of course not very efficient if you don't have a large team, you don't have a lot of expertise in database management, etc. So for startups, for companies which are starting out, who do not have a lot of these resources, they were often not able to optimize their workflows. Now, the idea of serverless, when you think outside of compute model, is basically that you define what you want, but how it is done, where it is done, and when it is done, all these things that the provider takes care of. In this case, when we are talking about database, you don't think that I need an EC2 T2 micro or EC2 Linux, this operating system for my database. You don't care about that, and you don't have to care about that. These providers, Amazon RDS, DynamoDB, and Neon, PlantScale, what they do, you mention you need a database, you mention the database name, you mention some kind of storage, etc., etc., and you only talk and care about your database, the management of your database, the maintenance, the sharding, replicas, whatever you just define, and the provider takes care of that. You don't have to explicitly manage the server that is typically linked to that database. Same way, when you're talking about storage, you don't say that I need an Linux operating system on top of an EC2 instant T2 micro with a hard disk space of 100 GB and I want to store my data there. You just say that I want 100 GB and I want to store my data there. And in pricing models of S3 and R2 technologies like this, they give you some amount of storage, and after you exceed that, you pay as you go. The more storage you use, the more you pay, right? That significantly simplifies the cost model, and of course the usage model also. You don't have to think about the servers, just only care about the features, the only component that you need. Same way with SQS. You only say that I need a queue, I need these features in the queue, and you have a queue which is exposed by AWS. Same with the notification service. So all these services, the common thing in them, the reason they are called serverless is because you don't explicitly mention what is the hardware, what is the operating system that is going to run and host these services. Just say that I need this service, and your provider exposes that service and it lets you configure different features on top of it. And that is the core idea of serverless. And since we are talking about serverless and databases, I want to come back to this part, serverless databases. But before that, we have to cover another important piece of technology, which is very important in understanding Next.js Vercel. But before that, we'll also understand serverless databases, but we have to understand edge runtime before that, so that we can cover serverless databases in a more comprehensive format. Yeah. So moving on, for this, we'll have to see some demo. I want to show something. So if we open the network tab here, and let's say we reload this page, and as you can see, initially our browser fetches the HTML document, then it fetches all the resources, different JavaScript bundles, the fonts, the images, etc., etc. This is how typical browser rendering a website works. If you look at the HTML document, you can see all the resources that are listed here, the style sheets, the images, the fonts, all the JavaScript bundles, etc., etc. And that's how your browser loads. It fetches the HTML, fetches the JavaScript, CSS, everything, and it renders that page. And that's how you can see a web page. Let's go to a different page because I want to show something else. So when we click on this and let's say we hit refresh and going back to the initial HTML fetching, you can see that here the time waiting for server to response, this is around 692 milliseconds because I have disabled cache so that we have more accurate timings. Now what happens when we hit refresh again, going back to the initial HTML document, you can see that the time waiting for server response has come down to 72 milliseconds from somewhere around 700 milliseconds to 72 milliseconds. In this section, we will explore why this happened. Why did we come down from 700 milliseconds to 70 milliseconds in one more refresh? Before that, let's clear up some basics. What is the biggest bottleneck when we are talking about latency, especially latency in data over internet? What do you think is the biggest bottleneck? The answer is the speed of light. And the reason is the fastest form of medium that we have, that we use for transmitting data from one point to another is fiber optics cable. Right? Fiber optics. With our knowledge of physics, the speed of light is one of the fastest form of medium in our universe, and it is around 300,000 kilometers per second. That is the speed of light in vacuum. Point to note here is this is the speed of light in vacuum. So this is an approximation. The exact would be somewhere around 290 something, but we are talking about approximation here. Now, since the light is transmitting inside a cable, inside fiber optics, which is one form of glass, and it has a refractive index of 1.5. Now you don't have to know or understand refractive index, but you can think of this as some kind of friction. It has to go through some kind of friction, and the friction amount is 1.5. You cannot get the complete speed of light inside a cable. Some amount of speed is reduced because of the refractive index of glass. And after that, we get the number of 200,000 kilometers per second in fiber optics. And this is the speed of data that we are talking about. Now, assuming you are from India and you want to make an HTTP request over internet to San Francisco. So from India to San Francisco, let's say, what is the distance? Distance from India to San Francisco. So it says around 12,000. So we can take around 13,000. And of course, 13,000 kilometers from India to SF. This is a straight line distance. Is the straight line distance. 13,000 kilometers is the straight line distance from India to San Francisco. Of course, this is not the exact distance because when we are talking about fiber optics cable, typically they are undersea cables that connects one country to another, and they have to go through mountains, they have to go through different city lines, etc. So a straight line distance is not a accurate measure, but we'll come back to that a little later. For now, we want to do a calculation. Okay. Now we are talking about 13,000 kilometers from India to San Francisco. So if we want to make an HTTP request, which will travel from India through cables to San Francisco, what will be the latency for one-way trip? For that, what we can do, we can divide 13,000 by 200,000, which is the speed of light in fiber optics cable. So we get around 0.065. In milliseconds, it will be around 65 milliseconds. Now, before this, as I said, a straight line distance is not fair because fiber optics cables that connects different countries, different data points, different ISPs, exchange points, etc. They have to go through a lot of stuff, a lot of blockers, and there'll be mountains, city lines, countries, a lot of congestion, etc., etc. So 65 milliseconds is not the exact figure that you are going to get, because that is a figure from a straight line distance. So from 65 milliseconds, taking all these different factors, the roundabout distance and the congestion in traffic, because your request is not the only thing that is traveling in that cable. A lot of other requests are also traveling, and requests have to be routed from different paths when there is a lot of congestion. And there are a lot of algorithms that are in place which take care of all this data routing, etc., etc. So taking into account all of this, right? All of this, we want to come to a figure. Let's say we take it 120 milliseconds. Take into factor everything: the distance, the roundabout distance, the congestion, the hurdles in traffic, everything. So making one trip from India to SF, we are making one request. The time it takes for that request to go from India to San Francisco, it is 120 milliseconds. Now, of course, since we are talking about HTTP, one request is not going to cut it. You have to make multiple requests, especially the first phase of HTTP is a TCP handshake, which means first you make a SYN request and then another acknowledgement comes from that side. So now again, we are talking about 120 millisecond. Now another request goes from here, another 120 milliseconds here. Now, finally, your server starts responding with whatever that you asked for. And if you ask for an HTML page, then it starts responding from this point up until here. From the first request to here, nothing was happening. It was just a TCP handshake, but you're still incurring the latency because that has to happen. The round trips have to happen. So what was the total amount? We have 120 here, 120 here, and 120 here, and then 120 here. So you have around close to 500 milliseconds of latency here for our client to get the first response. Assuming that this was a static asset and it did not have to do any kind of computing on top of it, because otherwise that will add additional latency of in another 200-300 milliseconds. Now, talking about this simple scenario where we are just making an HTTP request and we just want a very simple HTML file. In that only we incurred a latency of 500 milliseconds. Now, that is something we are stuck with because speed of light is a component that we don't have any control over and we don't see anytime soon that we can improve on. And that is the reason that is one latency factor that we are stuck with and we cannot do anything to fix it. What can we do to get around that limitation? Because of course, if one request is going to take 500 milliseconds and each request after that one round trip is, let's say, is going to take around 240 milliseconds, then user experience over the web and the speed of browsers, everything is going to get affected. And that is not a good experience for servers, for users, for everyone that is involved. So what can we do to get around that limitation? What do we have? Now, the only thing that we can do here is, since we don't have any control over the speed of light and the improvements of fiber optic cable are not going to have any significant impact on the speed of data transfer, right? At least not anytime soon. That's the reason the only solution that we can think of in IT industry is reducing the distance. If your request does not have to travel 14,000 kilometers to the origin server to get the first response, to get any kind of data, let's say it only had to travel around 100 kilometers or 200 kilometers max, or 1,000 kilometers, is significantly less than 14,000 or 13,000 kilometers, right? Then we can significantly improve the latency. The latency that was initially 500 milliseconds, that will come down to, let's say, 40 milliseconds and 50 milliseconds, and which is a significant improvement. And this is exactly the kind of reasoning with which people came up with the idea of CDN. CDN, which is also known as Content Delivery Network. This is what content delivery networks do.